Hello everyone. This spreadsheet that we're demonstrating goes along with the balance point spreadsheet that was demonstrated earlier. It's balance point temperature scenarios. So set up in the spreadsheet already are a couple tables that show you for a building with an average R value of the entire envelope, if we just average everything, they'd have an average R value of 5, which is poor. And if it was a length times width dimension with floor to floor height of 15 feet, and it had this aspect ratio, if you will, the internal loads are set at 2 watts per square feet. We have 1 air change per hour by either ventilation or infiltration. The sum of the UA, this is a coefficient that tells us the overall conductance of the entire envelope. That's the opposite of the insulation value. It's the inverse of insulation. It's conduction. The infiltration loss coefficient, the internal heat gain, because we already have this number here in watts per square foot. Here it is in BTUs per hour. Then this is a look at the resulting balance point temperatures across this range of scenarios. And see, the only thing that changes is the aspect ratio. But the balance point changes accordingly. Now, there are a series of these tables. This is for average R value of 5, an average R value of 10. If we scroll over, average R value of 15, 20, 25, and 30. Then there's an open table where you can enter your own values. Please note, I had to change the colors here real quick, but please note that the only values you're going to change are average R value, the aspect ratio, the internal load coefficient, the air changes per hour, and the rest of these values are calculated for you, including the balance point. You don't have to change all these scenarios. You might just use one line here to develop your own balance point. What it's going to tell you is what kind of an average R value you need, what kind of an aspect ratio of the building in terms of its shape efficiency, how your internal load magnitude is going to impact, and how your air change ratio is going to impact that balance point temperature. Bear in mind, there's no such thing as a good or bad balance point temperature inherently, because having very high R values will lower the balance point, but also having very high internal gains will lower the balance point. So you can't tell, strictly speaking, from the balance point what's going on. You have to understand the interplay of these other things. Thought that might help you see some of how these factors impact balance point temperature. Remember again that this is somewhat like your own personal experience of comfort level. You're comfortable when you're at thermal equilibrium, when the losses from your body, where you're generating heat metabolically, digestion of food calories, where your internal heat gain is equal to your heat loss to the environment by conduction, convection, radiation, and evaporation. In other words, by heat loss through your insulating clothes level, through your respiration, perspiration, through conduction, which is fairly rare, and through radiation to the surfaces around you. So as you become more active, generate more internal heat, you have to be cooler. You need a lower outside balance point temperature to be comfortable. As you wear more and more insulation, it has to be cooler for you to be in thermal equilibrium. Thermal equilibrium balance point temperature is the temperature at which you would be, by analogy, in equilibrium with the outdoor environment. You'd be losing heat as fast as you produce it metabolically, and you'd be comfortable. For a building, it's the outdoor temperature at which the losses through the skin and through air change is equal to the internal gain from people, lights, and equipment. Thank you.